For this lesson, we will concentrate on the conversion from decimal to binary and binary to decimal. But it's more important at this stage also to understand the nature of a numbering system, especially when it comes to the base. What does a base mean when we have a number? So let me just write down the objectives, what we want to do. We want to be able to do binary to decimal conversion. We want to be able to do decimal conversion to binary. So this will be our final outcome out of this. Okay? So first, let's understand what a number is. Let's say I have this decimal number, something we're familiar with. Let's say we have 263. Now, if I put D, that means it's a decimal. If I write 263 and I put a 10, again, that is a decimal number. Typically, if you don't put in this little indicator here and you write 263, then it is assumed to be a decimal number. Okay, so let's work with this number here that we're familiar with. And as you can see, 10 is the base. So this is the base. Okay, so D, deca, decimal, means 10. Okay, so now let's look at 263 and try to understand what it means. Well, 263, you have 3 digits. Each one has a different weight. So if you have to break it down and decompose it, and then recompose it back to its original form, then we could say that my 3 here is 3 times 1. And then what you're adding to that is 6 times 10 plus 2 times 100. Now, we're familiar with this. This here are the weights, right? So it has a weight of 1, this has a weight of 10, and this column here has a weight of 100. Okay? Now, let's talk about this in terms of the base. So we're going to do the same thing. So I'm going to rewrite this right here, and using the base and an exponent. So 2 times 10 to the 2. So just count how many zeros you have here. That would be your exponent. And then plus 6, 10 to the 1. Plus 3 times 10 to the 0. You have no zeros in here. By the way, if 10 to the 0 is always 1, or n to the 0 will be equal to 1. All right, so it's very important to understand that if you raise something to the power of 0, it's basically 1. So the factor or the weight is still 1 here. This is still 10, and this is still 100. Is just the way I'm rewriting it, okay? So I can incorporate the concept of the base raised to an exponent, right, to n, right, to whatever it is that you're raising it to, okay? So if you had to rewrite this, so what do we have here? We have 200 plus 60 plus 3, and if you add these numbers together, you will end up again with 263. So what we have done technically here is a conversion from decimal to decimal using the weight system. Fantastic. So can we do the same thing in a different numbering system other than decimal? The answer is yes, as long as you use the base to evaluate the weight of each column or each digit within that number. So let's do an example with binary. So this was decimal. Okay, and now we want to look at a binary number and do the same thing. Now, binary numbers, right, are a collection of ones and zeros. Okay? If you have a single digit binary number, it can either be 0 or 1. If you have two digits, it could be 0, 0, 1, 0, or 1, 1, or 0, 1. These are the kind of combinations you can get. Now, I haven't counted properly here, so if I have to redo this properly, it should be done this way. 0, 0, 1, 0, 1, 1, 0, 1, 1, if I had to count down. This being a value of 0, we will see this again. This being a value of 1 back in decimal, so if this was decimal, and this being a value of 2 in decimal, and this being a value of 3 in decimal. So again, we will see this, how it's done. First, let's concentrate on the binary number itself. So let's say I have a binary number written up this way. 1, 0, 1, 0, 1, 1. And I put either a B or a 2. So the same number can be re-expressed as 1, 0, 1, 0, 1, 1 with a base of 2. Okay, now can we apply the same rules or the same rule we did with the decimal? Absolutely. So we're going to take the base to the power n, whatever the position we're in. Well, let's write P for position. So P represents the position you're in. And now let's talk about something important when it comes to numbers. This digit right here is going to be called the least significant in our case, we call it bit. You can call it digit if you want, but it's very specific. These are bits. Okay, so one element here, a bit can be either 0 or 1. And this here is the most significant bit. Now, there's a shortcut for this. Some people call this one the LSB for least significant bit, and this is called the MSB for the most significant bit. Okay, so that means the least significant bit, the position always will be 0. So 2 to the 0, 2 to the 1 for the next one, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth. Aha! Can we rewrite it the way we saw how we decompose the decimal values? Yes, I'll take this one right here. Right? Or we could start from here. Let's start here. So we know 1, so the content of that digit times, okay? And that would be 2 to the 0 plus 1 times 2 to the 1. So that digit is represented here. So again, the base to the power of the position. Okay, so this is position 0, position 1, position 2, position 3, position 4, and 5. Well, let's see what happens here for this one. Right, so this would be 0 times 2 to the 2 plus 1 times 2 to the third. And let me just go over here, plus 0 times 2 to the fourth, plus 1 times 2 to the fifth. Right? So this would be the decomposition right here based on the weights. So let me rewrite it here. So we have 1, 0, 1, 0, 1, 1 as a binary number. So we could put a B here, right? And it's decomposed as, now remember, 1 times 2 to the fifth will be a 2 to the fifth. So 2 to the fifth. Now let's look at this one. 0 times 2 to the fourth. Well, that's 0. We can skip that one, right? So you're going to add 0 to something. You might as well skip it. How about this one? Well, that's 2 to the third. Plus again, we have a 0 here. We're going to skip that, right? And the next one is 2 to the 1. And again, 1 times 2 to the 1 is still 2 to the 1. And then plus 2 to the 0. Fantastic. So now what we're going to find ourselves doing is a binary to decimal conversion. So that means we're going to go from this to some decimal value based on the result that we get out of completing this equation. Now, how do we complete this equation? Now, if you're not familiar with the progression in terms of powers of 2, I can quickly write here a sample that would show you up to a certain point where you get. So 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3rd, 2 to the 4th. So you could use this as a reference table. 2 to the 5th, 2 to the 6th, 2 to the 7th. So I have 8 bits here. So this is pretty good most of the time to figure out what is the equivalent value in decimal for each one of these. And then we can add them up. Now, these are powers of 2. So they're very easy in terms of how they're going to progress. Remember, 2 to the 0 is going to be a 1, always. Remember this? We just did here? Excellent. So 2 to the 1 is a 2. Okay? So basically, you raised 2 to the power of 1. It's 2. Now, this is 2 times 2. So that's a 4. Okay? Now, a lot of people make mistakes and thinks this is 2 times 3. It's not. It's 2 times 2 times 2 times 2. 3 times. So if you want to look at this progression, these are powers of 2. Right? So what do you think the next number will be? Well, that would be an 8. Right? And what will the next number be? That would be a 16. What would the next number be? That would be a 32. What would the next number be? That would be a 64. What will the next number be? That would be a 128. Okay, you can pull your calculator and actually verify these values. Okay, so you can use this as a reference to quickly translate what you're looking at right here. So to do that, we can go to the 2 to the 5th, that's 32. And then we can go to the 2 to the 3rd, that's plus 8. And then we have 2 to the 1, which is what? 2. And then plus 1. Right? So what do we have here? We have 10, 11, right? 11 plus 32. So just add 1 for each one, so 43. And that would be 43 in decimal. So this value right here is 43 in base 10 or in decimal. So what we have accomplished here is a binary to decimal conversion. Let's do a quick example. Let's say you have this number. Let's do another example right here. Let's say you have just a smaller number, 111 in binary. What is it equivalent in decimal? Well, we know this is in position 0, so that's a 1. This is in position 1, so that's a 2. And this one is in position 3, right? Right? So that's a 4. Okay? I'm sorry, position 2, if 0 is a position, right? So position 0, position 1, position 2. So what do we have? You're going to add these up. Okay? So what do we have here? We have 4.2 is 6 plus 1, 7. So this is 7 in decimal. Okay? Now let's take another number, 101. And we want to convert it to its decimal equivalent. Okay? So same thing. Look at this reference here. This is position 0. That's a 1. Position 1, it's a 0, so you're going to leave it alone. Or you could write 0 if you want. And this is position 2, which is really the third column, right? So that would be a 4. And 4 plus 0 plus 1 is 5. Okay? Excellent. So that's how you convert from binary to decimal. There are other ways to do this conversion, but this is the most straightforward way to do it, as long as you remember this. And most of the time, you really need to remember up to 8 bits. You're going to find out why later on. It's very convenient. We could use this also in networking when we're doing IP addressing. It's going to come in really handy in terms of interpreting any of the IP addressing schemes we use. But in computer hardware, everything is byte-based. Byte is 8 bits. So this is very significant in terms of understanding what each byte might represent. Okay, so in our next video, we're going to do the decimal to binary conversion, and we're going to use a totally different technique on how to do this. I will see you then.